Welcome. We are solving the diffusion equation numerically. So, we are looking at the discretization scheme. Let us look at the diffusion equation that we are trying to solve. Okay, we are trying to do the implicit discretization. How does that work? Ci at time t plus delta t minus Ci at time t divided by delta t is going to be equal to d by delta x squared. And then we have Ci minus 1 t plus delta t plus Ci plus 1 t plus delta t minus 2 Ci t plus delta t. So, everything is at t plus delta t. So, that is why it becomes an implicit scheme. So, multiply delta t here by delta x squared, that quantity is what we are going to call as alpha. So, we have Ci t plus delta t multiplied by 1 plus 2 alpha, and then minus alpha times Ci minus 1 t plus delta t minus Ci plus 1 t plus delta t is going to be equal to Cit. Of course, it is written vectorially. So, you will have this C at time t vector is equal to C at time t plus delta t vector, that will be multiplied by a matrix, and the matrix terms look like minus alpha, 1 plus 2 alpha and minus alpha general. So, we are not going to have the first point line at all. So, this we are going to remove, because we know that 1 t plus delta t and C 1 t, it is the same, this value remains unchanged. So, we are going to, so if you have 101 by 101, that is what you have initially, because this is 101 by 1, this is 101 by 1. So, that is going to reduce to 100 by 100, right, because one row, one column is going to go away from everywhere. This also becomes 100 by 1. So, that is why 100 by 100 is what is relevant. We still have a problem, because when you come here, so 1 plus 2 alpha you have a minus alpha to the right of it, which is not there, but you have a minus alpha here, that is going to become minus 2 alpha. Why? Because remember, when we did this implementation of dou c by dou x at L equal to 0, that implied that Ci minus 1 and Ci plus 1 at this point is the same. So, Ci plus 1 was replaced by Ci minus 1. So, it becomes 2 times alpha times Ci minus 1 just for that last point. So, only for the last point, that is, if you have a 100 by 100 matrix, then this is the 100th row, 99th column will be minus 2 alpha instead of just minus alpha, because there is no point beyond 1 plus 2 alpha. In the others, the diagonal term is 1 plus 2 alpha, to the right and to the left you will have minus alpha minus alpha. So, if you do this, let me call this matrix as some A matrix, then you have in terms of matrix equation the following equation. What do we have? We have the matrix equation which goes something like this. It says A matrix multiplying Ct plus delta t is equal to some Ct. So, if I want a Ct plus delta t, all I need to do is inverse of A, and that should left multiply this C of t. This is a matrix multiplication, right. So, this is typically written as A inverse Ct. So, that will give you Ct plus delta t. Okay. This lines that I am drawing is to indicate that these quantities that we are talking about are matrices, they are not just numbers. Okay. So, this is what we are going to implement numerically, and you will see that inversion of A is very simple, and there is also some shortcut notation to do these things, because otherwise if you are writing your own code, this is the key part of the solver, inverting a matrix and left multiplying it to the right hand side to get the solution, but that is going to be fairly trivial when we are using Octave. So, let us write a script in Octave to solve implicit no flux 1D diffusion equation. Okay. So, I am going to, as usual, open in gedit a file. I am going to name the file as implicit no flux 1D diffusion. Okay. File new. So, I am going to save as, I am going to change just that, right, explicit I am going to change as implicit, right, implicit no flux 1D diffusion dot OCT, that is what the new file is. Okay, so, we are going to do the same thing as we did earlier. So, the first thing to do is to clear all the figure and clear all the variables that might be there, because you know, I used hold on. Now, if I go run this script, the figure from the other script is still there. This is also going to plot on the same plot, which I do not want. Okay, so, I want to start it afresh. So, I am going to start, let us say CLF, that is the first, clear all, that is the second step. And then as we did earlier, I am going to define some delta t is equal to 0.1, delta x is equal to 0.5. The reason why I am rewriting this and I am not taking the older file and edit it is because if you write it a few times, then it is better, you get better practice. So, I am going to write, but later we will just take the file, make the modification and run it. Okay. So, for now let us take it, and then the diffusivity is taken to be unity. I am also going to define this quantity called n, which is equal to 101. So, as you know, 101 is the size. Okay. So, I am going to define alpha. What is alpha? D times del t divided by del x into del x. Okay. So, this is alpha. Now, we are going to get the initial profile. So, how do we get the initial profile? We define C is equal to zeros with n rows and 1 column. So, that is how we make the vector. Remember, last time we did not define this n, we directly wrote 101 comma 1, that is possible, but you can also define variables. Okay. For those of you who have done programming, it is always a good idea to define the variables, because later if you want, you can just go change the n value here, everything will correspondingly change. Okay. So, I am going to make C of 1 is equal to 1.0. So, this makes the initial profile. The first point has value of 1, the rest of it is 0. Of course, we are going to define a new variable. Why is this important? So, let us go back and look at this a little bit more carefully. If you look at the vector equation that matrix equation that we are going to solve. See, in the earlier case when we did explicit, we just said C of I is equal to something, because the left hand side was all previous time and the right hand side was all previous time, left hand side was all new time, and there was no interaction between Ci and Ci plus 1 etc. right. If I calculated for example I equal to 2, the new I equal to 2 was on the left hand side, everything related to the old time was on the right hand side. So, you just got the solution. But when you are solving matrices, then there is going to be interaction between which is old and which is new. So, you need to keep the distinction between which is from the old time, which is from the new time. To do that, I am going to define a C old and a C or C new. Okay. So, the C old is equal to our CT. Okay. The C that you are going to get is basically C at time t plus delta t. So, at every time step we are going to take the current C and we are going to make it C old, so that the future time step you can get the new C. This is important because in implicit scheme we are trying to do it using a matrix multiplication, and then you need to keep the distinction between which is from the old time, which is from the new time. In the case of explicit, it is just an algebraic expression, it does not interact with the other C's that you are calculating. So, you can do it using the same variable, you can store the new result, but here it is not possible. So, let me do that. So, I am going to say for j is equal to 1 to n, C old j is nothing but C j, end for. Okay. So, now I am going to plot C with a red line, and then I am going to call that as initial profile, right, C, and there is and then I want to plot it with, this time let us not plot it with a line, let us plot it with some star. Okay. So, this is the plot. Okay. You can beautify the figure if you want. So, I get the handle on the axis, and then I say GCA set GCA line width 2, right, set AX, no, AX is the GCA. So, set AX line width is 2, and I also make axis as a square, because typically I like the figures to have square axis. Then you have to say hold on. Okay. So, till now whatever we have done in the earlier case is what we have done in this case also, except for two small changes. One is that we have defined a new variable called C old. Unlike in the explicit case, we are not using the same C to store t and then t plus delta t, because there it was done sequentially. Here everything is done at the same time. So, you need to keep the distinction between what is old time and what is new. Second thing is, while plotting the initial profile, there it was plotted as a line. Now, I am plotting it with some stars, so that you will see even on the x axis when the initial profile is plotted. So, that is the reason why I have done it. Okay. So, now I am going to make the matrix. So, let us define the left hand side matrix. So, how do we do that? We say A, of course, zeros works, because we know that zeros is the way to define matrices. And how big is this? This is n by n, right. Okay. And then, so I said that the first point you do not need to do anything, right. So, I have now got a matrix, which is the left hand side matrix, which is what has to be inverted and multiply the right hand side. And it is far more easier when you are doing the matrix inversion and things like that, to keep the complete matrix, otherwise you have to get rid of the matrix, then the vectors have to be changed in size, and then they have to be put together for plotting the solution and all that. So, I am going to avoid all this by making the first row, first column, the diagonal term, that is the A11 to be 1, the rest of that line is 0, in which case the action of that particular row and column on the vector is that it will leave the first term unchanged. Okay. So, that is what we are doing. A of 1 comma 1 is equal to 1. Okay, I have defined this. What is this? This is nothing but the implementation of the first boundary condition, namely that at location x equal to 0 or I equal to 1, the composition always remains the same at 1. So, we have defined that composition to be 1, and A1 comma 1 making it 1, and leaving the other terms in that first row and the first column to be 0 means nothing else will change. So, the composition at position x equal to 0 will remain the same. Okay, so, that is what we have done. Now, for the rest, for j is equal to 2 to n, right, for j is equal to 2 to n, what should we do? A of j comma j is nothing but 1 plus 2 times alpha, right, end for, right. So, we are trying to define this matrix. Take a look at this matrix. What was this matrix? The diagonal term, right, this term I made it as 1, the rest is 0. So, that 1 multiplying this will be this, nothing else will happen. If there are any other terms, then it will mix these terms with that, because they are all 0, then 1 will just multiply this and put it here. So, it is not going to do anything, right. So, now all the other terms 2, 2, 3, 3, 4, 4 etc. should be 1 plus 2 alpha, that is what is being done in this code. So, I have taken j 2 to n, the diagonal terms a j comma j is basically the diagonal term, it is 1 plus 2 alpha, right. So, now what happens for j 2 to n minus 1, because remember when we are doing the terms to the right of the nth term and left of nth term, there is a problem. So, that we want to do separately, because that is the imposition of the second boundary condition. For all the other points starting from 2 to n minus 1, you can make a j minus 1 to be equal to minus beta, okay, minus alpha. Right. So, this is the terms to the left, okay, except for one term which is a n comma n minus 1, that is equal to minus 2 times alpha, right. So, what is it that we have defined? Again, let us go back to the matrix I have defined all these terms, right. The second one will have first, and the third one will have second, fourth one will have third, etc. I will have minus I minus 1, which is minus alpha, except for the last one, and for n minus 1 is basically minus 2 alpha. So, that is what we have defined. Now, we have to go and define the upper diagonal terms, okay, terms to the right of the diagonal, okay. So, that we are going to do, define the upper diagonal terms. So, maybe it is a good idea to put here the comments. So, populate the diagonal elements, right. Now, here populate the lower diagonal elements, right, of the A matrix, okay. Now, let me populate now upper diagonal elements. Okay, so, I am going to say for j is equal to 3 to n, okay, a of j minus 1 comma j is equal to minus alpha and for. Okay, so all the terms to the upper diagonal, so we have obtained it, and remember, so it is important to know this runs from 2 to n minus 1 and this runs from 3 to n, because it is n minus j minus 1 and j. So, okay, so that is what the points are going to be. So, we have end for. Okay. Now, we are going to use the same idea of 3 loops, one for plotting, other one for time stepping, and the last one in the explicit scheme we had a loop for doing the computation itself, that is not needed. So, we are going to have only 2 loops, one is for plotting, other one is for time stepping. The third loop, which was actually for evolving, is now replaced by a matrix operation, inverse of A multiplying the C old, which will give you the C new, and at the end of that we make the C new as the C old and we proceed with the iteration. So, that is what we are going to do. So, let us do that for k is equal to 1 to 20. So, let us plot 20 for j is equal to 1 to 500. So, every 500 steps once we do, what do? We say C is equal to inverse of A multiplying C old. Okay. So, this is a way. There is also another way, which is A slash C old, that will also get you the same solution. We will talk about it a little bit later. So, then what do? So, remember, so this loop we have not ended. In this loop we first take, so this is for time stepping. So, one time step we have done. After that, what do? We say for I is equal to 1 to n, C old I is basically C I and for. So, whatever C I have calculated, I make it as C old, so that I can go for the next step. So, this is loop for I, right, which is basically to store the old new value, to store new C in old C. That is what this loop does. Then end for, this is loop for J, right, because it calculates once for J equal to 1, for example, it will do, and then it will take that to be the old C. So, it will go, it will do 2. So, another time step is done, it will save that new C as the old, so that it can go to the third time step and so on and so forth. Then of course, we have to plot C, and we have to end the last loop. So, this is the loop for k that we end, and of course, we print the plot, print minus d. So, let me plot this, save this file as djpg, that is print to device called jpg, implicit no flux dot jpg. Okay. So, I am going to save this, then we go and we run the code, right. So, this time it was not explicit, it was implicit, right. So, let us run, there is a problem. Okay. So, let us go look at what the problem is. It says attempted to use a complex scalar as index, okay, assignment failed, error called from in this code at line 46 column 10. Okay. So, this is a good thing about the error messages, because when it gives error message, it tells you clearly which line, which column it has a problem. So, let us go look at line 46, line number and column number are given here at the bottom. I hope you can see my mouse. So, the line and column numbers are given here. Line 46, it says, and I have made a mistake. See, this is capital J, right. It should have been small j. It does not know what that capital J is, and that is the reason why it gave the error message. So, as you can see, and that is line 46 column 8. Okay. So, it can give you quite accurate, see it said line 46 column 10, it was quite close to that point where the equal to sign was, and that is where it was complaining. So, one of the things that you have to learn when you are writing script or programming is that you should be able to read the error messages that your computer is giving you and understand what it is and go back and correct it. Okay. In my definition, a programmer is the one who can carry out a conversation with the computer. You will do something, computer will tell you something, then you should be able to understand what it is and go correct it. Typically, first time programmers tend to copy paste the error message in Google and try to solve. That way, you will never become a good programmer. Okay. You do not need an intermediary to talk when you have to talk directly with the computer yourself. Okay. So, it is a good idea to read the error messages carefully, try to understand yourself what it means, and this is just practice. Every time you get an error message, go try to locate the error yourself. It is like a puzzle. Okay. So, it says there is something wrong with that line, what is wrong? So, you go figure it out, and that is how your programming skills will improve. So, let us try to run again. Okay. So, I still have a problem at line 51 column 3. Okay. So, let us go and look at what is wrong with the line 51 column 3. Okay. I do not understand what is the problem here. Okay. So, it says line 51 column 3 is some error. The operand 1 is 101 by 101, operand 2 should be 101 by 1, but it somehow thinks that it is 1 by 101. Okay. I do not understand why it is so. So, let us go back and try to do this other exercise. Let us say there is another way of doing the same thing. C is a /old. Let us see if this works. let me see if this fixes my problem. Maybe it does. Yes, that does. Okay. So, if you are here, you will hear my computer making lots of noise. The reason is the explicit method is very, very computationally simple. The implicit method is quite costly. Okay. It has to do this inversion of a matrix, and that is not easy. Okay. So, my computer is actually making lots of noise at this moment, it is struggling, but it got the solution, and you can see the solution like in the earlier case. So, you have 1 and then you have this. So, the red points are basically the initial profile. So, it starts from here and it is like this, and as time proceeds you are having this composition profile which is changing. And like in the earlier case, of course, the boundary condition is the same, whether you solve it using implicit or explicit does not matter, it is going to show you the same solution, and of course, it is showing you the same solution. Okay. Now, you can actually go and put ls. So, you can see that implicit noflux.jpg is figure saved, explicit noflux.eps is another figure saved. So, these figures are saved in the same directory in which you are going to invoke the scripts. When the script is run, the figures are generated, a copy of it will be saved in the same directory for your future use. So, we have done today using implicit and explicit scheme for one boundary condition how to solve the diffusion equation. So, in the next lecture we will go ahead and solve for, let us say that at the left end also you have a Dirichlet boundary condition. Okay. So, what happens? So, suppose I say that the left end it is always kept at some composition 0, it does not change. Whatever material that comes, then what will happen? The material will escape from that point, and the flux will be determined by how much material is coming in, because the composition has to be at 0. So, whatever amount of material that is coming in should escape. So, that will determine the flux. So, you can give Dirichlet boundary condition at the right extreme end also, and we will do that, and we will solve again that using implicit and explicit scheme, and that will be the topic for our next lecture. Thank you.